We now consider stochastic interest rate models. In the first part, I provide the basics in stochastic calculus that is needed for developing stochastic interest rate models. We will then look at short rate models where the dynamics of the short rates is specified. And in the second step, we look at so-called Heath-Jarrell-Morton models where the evolution of the entire forward curve is specified as a stochastic process. Eventually, we will see how these models can be used to price options on bonds. In this first part, I recap the basic notions of stochastic calculus. That is Brownian motion, the stochastic integral, Ito formula, the Girzanov theorem. Obviously, we cannot go into the mathematical details. But the good news is, once you acquire the rules of stochastic calculus, you can engineer any of the following interest rate models. I will also, in this part, give you the basics for pricing options, namely the arbitrage pricing theorem. We always fix a stochastic basis. Random variables are modeled on a probability space. This is a triple consisting of the set of samples omega, and on this set of samples omega we have a structure which is called a sigma algebra, which is denoted by calligraphic F. This is the collection of the so-called measurable events. The probability measure P acts on the sigma algebra calligraphic F, and it assigns a probability to any measurable event A. The flow of information is modeled by a filtration. This is an increasing family of sigma algebras indexed by time t, and ft represents the information available by time t. Let's look at the following example, which consists of a sample set consisting of 4 samples. Suppose the probability assigns the same weight to each sample. We have 2 time periods. At terminal time 2, the true state of the nature is fully revealed. However, at time 1, we can only tell whether we are in the set consisting of omega 1 and omega 2 or in the set consisting of omega 3 and omega 4. So the sigma algebra F1 consists of the 2 sets omega 1, omega 2 and omega 3, omega 4. At time 0, the sigma algebra is trivial. We cannot distinguish any of the samples at time 0. A stochastic process is a family of random variables indexed by time t. We usually suppress the argument omega. We call the stochastic process adapted if for any fixed time t the random variable xt is ft measurable. We call xt a martingale if it is adapted and such that at any time small t, the conditional expectation of the future values at some time point capital T is just equal to the currently prevailing value. A martingale is a model of a fair game in a sense that on average you cannot gain more than what you have today. As an example, consider again the stochastic basis from the previous slide, and let's assume that xt models the price of a financial asset at date t, and assume xt is adapted. In the 2-period context, that means at terminal time 2, we know the terminal price, which is a function of the state of the world. At time 1, we cannot anticipate the future, so the asset price must be the same in the states omega 1, omega 2, and also it must be the same in the two states omega 3 and omega 4. At time 0, we have no information yet, and the asset price is a constant. The prototype of a martingale in continuous time is a Brownian motion. A standard Brownian motion W is characterized by the following 4 properties. It is a continuous and adapted process. It starts at 0 at time 0, and its increments, Wt2 minus Wt1, are independent of the past and normally distributed with mean 0 and variance proportional to the time increment. As I already said, the Brownian motion is a continuous martingale. The figure on the right shows 4 trajectories simulated from a Brownian motion. All trajectories start at 0. As you can see, Brownian motion has rough paths. They are not smooth, they are not differentiable. And at any given point in time, the expectation of the Brownian motion is equal to 0. A Brownian motion is a Gaussian process in the following sense. We define a stochastic process Zt to be a Gaussian process if its finite dimensional distributions are multivariate Gaussian or normal distributed for any finite selection of time points t1 up to tn. Since the multivariate normal distribution is determined by its mean vector and the covariance matrix, it follows that the distribution of a Gaussian process Zt is determined by its mean function, that we call mt, and the covariance function, which gives the pairwise covariances of Zt1 and Zt2. For any adapted process sigma t, whose trajectories are square integrable in time, we can define the stochastic integral with respect to a Brownian motion. This is how we denote the stochastic integral. Even though the rigorous definition of the stochastic integral is a bit more involved, we can think of it as being the limit of Riemannian sums as shown here, where we go over partitions of time and let the mesh tend to 0. It can be proved that the stochastic integral is a continuous martingale if the integrand satisfies a somewhat stronger integrability condition. The stochastic integral will be the model for the risky part of the return of an asset. An Ito process xt is an adapted process of the following form. It can be decomposed into an initial value plus a drift term plus a martingale term, which is a stochastic integral. Remember that the Brownian motion, and therefore the stochastic integral, has rough trajectories. The drift, in contrast, has smooth trajectories and models trends in the evolution of x. An Ito process is thus the ideal model for the price process of a financial asset. We often use differential notation for x, where we omit the initial value and write as shown here. Keep in mind, whenever we specify an Ito process x in differential notation, there is always an initial value to be specified with it. Sigma is also called the volatility of the process x. It can be proved that if the initial value, the drift, and the volatility of x are deterministic functions, then the process xt is a Gaussian process with the following mean and covariance functions as shown here. It is easy to understand why the mean function is as shown here, because the martingale has zero expectation. We take for granted that the second moment of the martingale is given by the integral of sigma square ds. The core of stochastic calculus is the Ito formula. It states that for a C2 function fx, meaning the function f is twice continuously differentiable, and for an Ito process xt, which is given in differential notation here, the composition f applied to x is again an Ito process with decomposition given by that. It is important to see that real calculus would give us a total derivative that is underlined. But this would only hold if xt would have differentiable trajectories. Recall that the stochastic integral has rough trajectories which are not differentiable, which is inherited by xt, and that causes the appearance of this second order correction term. It also explains why this formula only works for C2 functions f. We need f to be twice continuously differentiable. There is also a multivariate version of Ito's formula, but I refrain from showing it here, with the following exception: the integration by parts formula. It states that for two Ito processes, x1 and x2, both in differential notation as shown here, the product x1 times x2 is again an Ito process with decomposition as shown here. Again, we realize that this is the product rule that we are knowing from real calculus, but that holds only if x1 and x2 had differentiable trajectories. Since they do not, due to the stochastic integral, we have the second order correction term showing up. As an example of Ito's formula, let's look at the exponential function applied to an Ito process x, which is given in differential notation here. The decomposition of e to the x is given by the sum of the derivative of e to the x, which is e to the x itself, dx, plus the second order correction term, which involves the second order derivative of the exponential function, which is again the exponential function itself. Again, we see here the fundamental differential equation that y would satisfy if xt would have differentiable trajectories. There is a counterpart to the classical exponential function in stochastic calculus. It's called the stochastic exponential, and it's denoted by calligraphic E. It is defined as shown here. It is now an exercise for you applying Ito formula to show that the stochastic exponential actually satisfies the fundamental stochastic differential equation, which corresponds to the fundamental equation that would hold in real calculus if x would have differentiable trajectories. This property of the stochastic exponential is very useful for two reasons. First of all, the stochastic exponential is positive by definition. This is useful because most price processes of financial assets are positive. And second, due to this fundamental stochastic differential equation, the stochastic exponential preserves the martingale property. That means, if x is a martingale, then the stochastic exponential of x is also a martingale. In sum, the stochastic exponential is the prototype of a positive martingale in stochastic calculus. In financial modeling, we often change the probability measure. This is why it is useful to review Bayes' rule. Let Q and P be equivalent probability measures with radon-Nicodim density denoted by dq over dp. Bayes' rule relates conditional expectations under P and Q. For any bounded random variable x, the conditional expectation of x under Q can be expressed as conditional expectation under P if we multiply the argument x by the radon-Nicodim density of Q with respect to P and normalize by the conditional expectation of the radon-Nicodim density. If we vary little t, then this becomes a martingale. It's called the radon-Nicodim density process. It is a positive martingale. The Girzanov theorem describes what happens to a Brownian motion under P when we change to an equivalent probability measure Q. The statement is as follows. For an adapted process lambda, satisfying some more technical conditions, the eta process called W star, given by the expression as shown here, becomes a Brownian motion under the equivalent probability measure Q, which is determined by the radon-Nicodim density process as shown here. This means if we are given a Brownian motion with a drift lambda dt under the measure P, we can detrend by changing the probability measure to an equivalent measure Q exactly when the radon-Nicodim density of Q with respect to P is given in terms of the drift lambda in this way. Here is a very important application of the Girzanov theorem in financial modeling. It's the arbitrage pricing theorem. It states that any traded asset with a positive price process denoted by S must have a return as shown here. That means the return is decomposed into a drift component and the martingale component. The drift component models the expected return. Its rate is the sum of the short rate, RT, plus a risk premium, which is of the form sigma times lambda. Sigma is the volatility of the return. The larger sigma, the more risky the return is. And lambda is the so-called market price of risk. In consequence, the more risky the asset is, that is, the larger sigma is, the larger is going to be the excess expected rate of return over the risk-free short rate. Recall that the short rate is called the risk-free rate of return because this is what the investor would earn if he would simply invest in the savings account. We now see how Girzanov theorem comes into the play. We can rearrange the terms, the excess expected rate of return and the noise part, as shown here. What we see here is the Brownian motion plus a drift. We use the equivalent probability measure Q as shown on the previous slide in Girzanov theorem, where we learned that this is a Brownian motion W star under the equivalent measure Q. We can re-express the asset price return as follows in terms of W star. We now see that under the equivalent measure Q, the expected rate of return is the risk-free rate R, while the volatility remains the same. We can thus restate the arbitrage pricing theorem by saying that there must exist an equivalent measure Q, which is called risk-neutral measure, under which the return of any traded asset has an expected rate given by the risk-free short rate. Using integration by parts and Ito formula, one can show that this differential notation is equivalent to what is shown here. It states two things. First, the discounted asset price process, discounted by the risk-free numeraire, the risk-free asset, the savings account, is a martingale under the risk-neutral measure Q. And second, this martingale is given as stochastic exponential of the martingale part of the return of the price process.